This video will begin our discussion of double integration. So let's relate it back to Calc 1, 2, just depends where you were introduced integration at, also depends which school you went to because it's broken up different ways. Anyways, okay, so if we had a graph in 2 dimensions, as you can see on the screen here, we would draw these rectangles here on our XY plane to kind of try to capture a feeling of the area. So we would put points here, and what we would do, instead of trying to find the area of that weird shape, we would create all these rectangles, and you can see that like the left side of each rectangle hits the curve. And then we would just find the area of those. Well, the area of those would be your change in x here, right? Each one, and it's the same. That's why we get to call it change of x in this case. We usually would leave it the same. We could do a bunch of different sizes. It didn't always have to be the same, but we're trying to approach the integral, and usually with the integral, to approach it theory-wise, letting those be equal tends to make it a little easier to see. The area of that rectangle is that change of x at the bottom times y. But y we would just write as f of x, and then we would want like different x's. I want this one, plug in that x to get that y, I plug in this x to get that y, so we call them x sub k's, and we would just like let each one, like number 1 here would be x sub 1, x sub 2, x sub 3, and so forth. And we could run it through, and you can see if we had n of these, if we'll look at this formula over here, let's just ignore for a moment the summation. Don't look at it. This is change of x. This is the base of each rectangle. This is the height of each rectangle. And then what the summation actually does is it runs us through every single rectangle, because it's going to put a different k in the subscript, running us through all these x's that are down here, right? And it adds them all up. This is just an approximation, but we learned in Calc 1, 2, depending where you were introduced, that if I wanted the actual area, I would just find the limit as the number of rectangles goes to infinity. And it would be that limit that would get us our integral. You could work this out in a bunch of different ways. These are very neat problems in calc books. The problem most of the time is that Calc 1 teachers just don't have the time to go through it. But that is how you would approach the integral, is with that limit, having rectangles. In Calc 3, we can use that same idea, and I'm not actually going to drag you through that theory because it gets pretty heavy. Your book will do a lot of it if you'd like to go and read it there. I'm just going to kind of capture it with some pictures. So notice that three-dimensional curve up here, A. We could actually break this down into rectangles, but instead of rectangles, we'll just do rectangular prisms. So we'd have that column in each place, and we maybe put the center of the cube of the, it's not a cube, but the rectangular prism, put that at the spot, so at the z value. So take a look. This will make more sense of what I'm trying to capture with my words. If we look down here, if I wanted to find the volume of that shape, I would need to start finding the volume of my rectangles, right? Rectangular prisms. Well, that rectangular prism, it's length times width times height, but instead of thinking that, let's just think length times width, we'll call that area, and then the height, we'll call it the output of our function, because that's what it's giving me, right? Like if I plug an x and y in here, I get a z value out, or here, I guess I could have looked there. So if we want to find the area of the bottom of our rectangular prisms, it's just the change of x times the change of y. We're going to call this, if we look down here, this is the change in area. So this thing represents the area of the base of each rectangle. So, and then the k in the subscript just runs me through each rectangle there on the xy plane. If I take that area and I times it by the up value, which is our output, is our z, that would give me the volume of that box. We would just let this value up here maybe be the center of the box. It could be one side of the box. It really could be anything we want it to be. The calculus will still get us to the same spot. Here's the summation for this volume. Okay, notice this is the area of a base, right? That's what we talked about over here. This is the output value, the up value, so that'd be my height. So I have length times width over here, and then I have times height right there. That would give me a volume of each rectangle. Well, if I add them all together, that is the whole shape. And then I'm going to go to the next page because I actually typed this line out. Number of rectangles, if we let them go to infinity, we have what is our double integral, right? So letting the number of rectangles would actually hit the volume exactly. So that's why we have equality instead of approximation here now. And this is the double integral. All right, so for a function, the volume under of a surface is the double integral over this R is just the region we're talking about. I know we haven't really seen like different things down there that hasn't been more like this. You're used to seeing integrals like that. This is just going to cover a region. So this is going to allow us to integrate over weird regions. We can integrate over something that looks like an 8 or a dinosaur or any shape that you could imagine. We could try. I'm not saying we could do it. A computer probably could figure it out if you could figure out how to type it in. But this is our volume under a surface over a region. So it could be how much grass is in your square backyard or weird shaped backyard. There's a lot of applications for this double integral stuff. Now there's a theorem, and we're not going to like heavily go over it or prove it or anything like that. It's called Fubini's theorem. What's really nice, remember that this dA here comes from letting this limit of the area go to infinity, right? Remember that if I take like the change of y over the change of x, and we let the change of x do some stuff, right, and we ended up getting dy dx, right? Same idea. So we get dA, but dA really is just dx dy or dy dx. Fubini's theorem says they're the same thing. I can do whichever one I want. Okay, a couple things I want you to notice here. These double integrals are really easy to understand, but up front can be a bit difficult. What is happening here is we're doing an integral inside, just like that. If you notice, if I cut that out and I only look, I could even zoom in. I'm not going to do that because I feel like I'm going to make people dizzy. But if I were to ignore this, I can do this instead. That's just a Calc 1 or Calc 2 integral, wherever you started learning them. Once I have that answer, right, I would have some answer. Let's call it A. Then all I would do is take this stuff and bring it down, and I'd have AC of A, whatever's going to come out of that, dy, and now I have another integral. Another Calc 1, 2 integral. Two-dimensional, I guess I should just say that. So it's the inside, get an answer, and then the outside. And it works like that. We're going to add actually more integrals later in a different section. You work from the inside out. So this one, we'd start with the y, right? We'd start integrating with the y, and then we'd get an answer, and then we'd integrate with the x. Let's get an example. It's a little easier to see. This is definitely something you want to see a bunch of examples of. So let's take a look at this first one. Okay, so first thing we're going to do, and I don't want you to skip the step. I know most of you like hate graphing with a passion, but we're going to be dealing with some weird regions later. So I draw my region. Even though this one's very easy to see, I want us to get used to drawing our regions. All right, so this goes 0 to 3 in the x, and then 7 in the y. 2, 3, 4, 5, 6, 7. Put a 5 there so I can see where that's at. I'll put a 3 here. And then our region, I'm going to put it in a different color. Our region is this rectangular piece here. I'm just going to go all the way and see if it'll connect it all for me. It did, but it's nasty. It's not going to do that well, so I'll delete. All right, so let me just get a straight line across here then. And then if I go straight down, so we're talking about the region inside of this thing. So that whole region in here, I'm not going to shade that in. I all of a sudden wanted to start to fill in all the gaps, but I'm not going to do that. So the region inside the rectangle. So how I think about this, imagine the shaded part there that I could have finished up. Some of you guys are it's probably driving you crazy. Imagine that being like your backyard, right? And that's the fence. What we're actually doing, we have some kind of surface. This is our x-axis over here. This is our y-axis over here. We have some kind of surface that's coming out at us or going down into the screen. That could be like the level of grass, right? Even though our grass should, I guess if you're cutting it, should be growing at the same rate, but it doesn't, right? We have different patches growing up and down. If I found the volume over this region, over your yard, it would tell me how much grass is in your yard. It would allow me to get a bunch of different heights that's sticking out of the screen at us. Okay, so the double integral is very easy to set up, thankfully. We keep the same integrand, which is the inside. And then we have to look at this and decide, is there an easier way? We're gonna integrate like a partial, but with respect to x or y, and we got to do one first and one second. I'm going to go ahead and do with respect to y first, and then I'm going to do with respect to x. Okay, now this is the important part to not mess up. Y goes from 0 to 7. We are doing y on the inside. Your book will not write these y's in. If you look online, they don't write them in. Please trust me that it's going to make your life easier later. We're going to put 3 integrals across there, and they're going to have different functions. It's not going to always be numbers. It gets very messy. So if you get in a habit of putting x's and y's, it won't be a big deal later when you start having to do it to keep things straight. All right, so x here is ran from 0 to 3. All right, so we just focus first on this integrand. That just totally kills the color. This integrand. We just do that first and leave the other stuff outside. Okay, so this calls for a u sub. We're going to let u equal x minus y, which means du. Okay, and we're only integrating, in this case, with respect to y, so the x is gone, and I got a -1 dy. Some of you guys solve, I think, for the dy in this case. Just depends on how your calc teacher approached it. I got -du dy. So I'm going to replace all that stuff. I don't really want to have to go back to... No, we'll just do that. Okay, so equal sign, we'll do... Let me write this. I'm going to shrink this down just a bit because I'm going to go over the next page if I don't. So it's a bad habit of mine. Okay. I keep my x equals 0, x equals 3. We're going to go ahead and let's go ahead and convert our y's. Let's do that. So remember, our y equals 0 here and our y equals 7. I'm just going to plug that into the u function, which means if I plug in y equals 7, I'm going to get u equals x minus 7. And then on the bottom, I'm just going to get u equals x, because plugging 0 would make the y go away. I'm going to plug this in now, cosine of u. I need to introduce the negative with the du, and then dx. I'm not even going to go back to y. You can do that, just depends on how you learned it, what you were comfortable with. I don't care how you approach it, just that it's correct. Okay, so x equals 0, x equals 3, nothing happened with that. So now I'm going to take the integral of negative cosine. Okay, negative cosine is going to be negative sine u. And I'm going to run that from u equals x to u equals x minus 7. I keep that dx on the outside. It did not go away. All right, I'm going to go this way. I got x equals 0, x equals 3, and now I got to plug that stuff into u. It's not pretty. It's going to be negative sine of x minus 7, and then remember we minus it, so it's going to be a positive sine of x. I'm going to put that in parentheses because it feels nice there. And then I got dx. Notice now I have an integral that is just in terms of x. At this point, us being in Calc 3, I actually don't mind, and if I change my mind later, I'll change my video. You can use a calculator right there and plug it all in and get an answer. I'm totally cool with that because we've done all the Calc 3 stuff. I would rather you practice your integration, if I had to be honest. But I know where we're going. Mostly in our fields, we're going to be using calculators and computers to do that. So if you would like to do it there, please do. I encourage you to get all the integration practice that you can. Most of you had to take DiffyQ after this, and it is very integral heavy. Very integral heavy. So get the practice while you're here. If not, use a calculator. Cool. Okay, so this is just, I separate it by terms. So I'm going to go ahead and do that. It could be a u sub here. But I know if I do it, that du is just going to be 1. So I'm just going to put x minus 7 back in, knowing that it takes care of itself. Okay, the integral of negative sine is just cosine of x minus 7. What I was just talking about, go ahead and take the derivative of that thing, and you'll see that you just get back to here. The x minus 7, if I take the chain rule of x minus 7, it's just going to, I'm going to multiply by another 1. I hope you can see that. Okay, the next one doesn't have the negative to cancel out, so it's going to be a negative cosine of x. And then we're going to run these from x equals 0 to x equals 3, and we're going to be at our answer. So I'm going to write a kind of small here because I got to fit quite a bit in. If I plug in a 3, I got a -4. minus cosine of 3. Then I have minus the whole second half. I'm going to put it like that. And we're just plugging in zeros now. So I got minus cosine of negative 7. And then minus cosine of 0. That's just a 1. I'm going to go ahead and change that. That's a great answer. I don't think we can clean it up much at all without getting decimals. I like exact answers because I'm a mathematician. Doesn't really matter if you go to a decimal. Unless I say, give me an exact answer, a decimal would count. Just don't round off. Like, you guys are future engineers, future scientists, physicists, mathematicians. Please quit rounding one decimal place. We need to go a couple, unless it's called more than a couple. I always go 4, and it really depends what we're talking about, right? If I'm talking about an astronomical unit, rounding off to 4 decimal places is a lot of miles. But if I'm talking in something micro units in some way, maybe 4 decimals is plenty. We just really have to read the room with that. I think the safest call when it comes to rounding is you don't chop it off with 1 decimal. Go 4. Go 3. 3 would be, I think, the minimum of the safe call, I guess. This is me being paranoid. If you're unsure why I'm being so paranoid about rounding, when you round in your problems, if you round too early in your applications, you could be rounding off quite a bit of distance, weight, and it may not feel like it because in the process you're only rounding off a little bit, but that stuff adds up. So if you've ever went to decimals and then checked your decimal with the problem in the back and it felt like it was quite a bit off, it could be due to your rounding. So go at least 4, 3 at minimum, but don't round too hard. I like this. This is perfect.